So I will be talking actually about the proximity-induced superconductivity in topological insulators, because this session is supposed to concern the superconductivity. So once again, it's a great pleasure to be here in Mainz and also to present this talk. And let me just start. So I will briefly talk about, remind you of what everybody knows, because topology matters here, about the topological insulators. So I will just briefly tell you why they are important and how to actually induce the proximity-induced superconductivity in these materials. And then I will talk a little bit about the thermal conductance, because the thermal conductance can be also the source which can tell you about this kind of topological edge states in these materials. And then I will tell you a little bit about how you actually can see this topological states, or Majorana states, or topological Andreev bound states also in the AC Josephson effect. Okay, so this is what you possibly already see many, many times. So the idea is that instead of talking about the relativistic electron in the relativistic lab and looking at the positron and electron band, we could actually look at the semiconductor. And the nice thing about it is that some of the semiconductors, especially narrow gap semiconductor, have the same structure like relativistic electron. So one can actually look at the valence band and conduction band and the gap between this, and look at the energy scale. And although the energy scale here is a little bit different, as well as the velocity is a little bit different than in relativistic systems, one can actually try to investigate the topological materials and topological property in the solid state lab. So what was already said yesterday in lectures before, or in talks before, is that if I have an inversion of band, so if I have, for example, some kind of material like bismuthium selenide or mercury telluride, where the heavy electron band is above the heavy hole band is above the electron band, then what can happen is that if I now actually take this material and I put it in respect to the vacuum, what will happen is that I will have nice gapless states forming at the boundary. And what happens moreover is that this, as we know very well, this edge states which are forming at the boundary, they are spin polarized and they are helical. That means that the direction of the motion of the electron is related with the spin polarization. So indeed, the topological insulator have a bulk gap, while at the edge or at the surface one actually have the edge states or the surface states which cannot be removed by the deformation. So let me skip the slide, because I already explained what are 2D topological insulators. So one can obviously also have a form of this topological insulators in the 3D, and then instead of having usual edge states like in the 2D topological insulator, one actually has the surface states, and in the surface states there is a two-dimensional Dirac Hamiltonian, again, which is gapless, which corresponds to the spin momentum locking. What is interesting as well about the 3D topological insulator is that if one actually wants to make a 180-degree backscattering, this is not allowed, because if I take a potential here, let's say scalar potential, and I would like to scatter between this point and this point, then additionally to changing momentum, I would also have to change a spin. And as long as I have a spin-orbit interaction in the system, there is no backscattering, so there is no 180 backscattering in these materials. And now this feature actually is the feature which gives me a new aspect when I put the topological insulator in respect to the superconductor. So let's say that I put S-wave superconductor in touch with topological insulator, and then I can actually get the consequences of these facts. Okay, so now it's one more slide when I can ask myself what's the difference between topological insulator and topological superconductor, and there is no so much difference in some respect. So what actually Majorana asked himself, if one can rewrite the Dirac equation, which has a complex field and the charged particle with spin 1/2. So this is obviously then the the fermionic relations are applicable to the topological insulator in a situation that instead of using the psi, he was actually used psi tilde with the real field. And then what happens is that one can have a neutral particle which has exactly zero energy, and where one can have situations that particles equal to the antiparticle. So this is indeed the topological superconductor. As you can see, these are very much two related objects, and actually one can also induce the topological superconductivity in the topological insulators. Okay? So this is exactly what I would like to talk about. So the question is, if I put a superconductor, S-wave superconductor, on the top of the 3D topological insulator, exactly in the proximity to the surface state, is what kind of superconductivity I will actually induce in my system. And I can actually write here an effective Hamiltonian. So this is Bogolyubov division Hamiltonian. So this is in the basis of excitations of electrons and holes. And one can see that I can actually write a part of the Hamiltonian which is related to the surface states for electrons, and part of the Hamiltonian which is related to the holes. And they are connected by the singlet S-wave superconductivity. So now one can, so this is exactly electron and hole surface state Hamiltonian. And this is the induced singlet pairing. And there can be also some spectrum shift of my system because of the tunneling. So, however, what is interesting here is that if I put, so let's say that I have a Cooper pairs tunneling from the S-wave superconductivity, and they are superconductor and they are singlets. However, because of the breaking of the spin rotational symmetry in my surface states, what happens is that I can change the singlet into the triplet. So what happens is that I will get, if I look, for example, at the correlations which are induced in this surface state of my topological insulator, they will have two components. So one component would be sigma 0, meaning this would be directly connected with the singlet, while the second component will be actually, I would call it helical, because the spin and momentum are coupled. So here is exactly sigma dot p, and this part of the component, you can immediately convince yourself, is related to the p-wave superconductivity. However, here we do not break time reversal symmetry. So it's actually the component px plus minus ipy. So the reason why one can actually get this correlation is, as I said, because in general, if the spin rotational symmetry is broken in a system, one can actually change the singlet into the triplet. Okay, so the question is now how to measure this triplet, and the point is that if you, as you can see here, you have two components. So you have a singlet component and triplet component in the correlations. So the question is how to distinguish between these two components and how to actually measure what you want, which would be interesting to see the p-wave component of the superconductivity. So the way we actually propose is to take a topological insulator and build a Josephson junction on this topological insulator. So what you do is you just put two S-wave superconductor, and then you have the normal regime, which is here a surface of topological insulator, and you put a gate over here. And then you ask, so this gate, as you will see, will be important here. And then you ask yourselves what kind of effect, what kind of supercurrent you can get through this material. So what is important is that obviously during this process you always go from the superconductor, you inject, let's say, electron, but then when you make again Cooper pair in the superconductor, you reflect a hole. So what you get is, if you make it many times and all of the states are in the superconducting gap, you get Andreev bound states. And that's this Andreev bound states, which might be also the topological origin, are of interest for us here. So what happens is, and that's what we did with Grigory Tkachov, we ask ourselves what could happen in this kind of system. And we know that from relativistic physics that in general it is possible that the electron can go through the barrier with the transmission of one. So here we have something similar, however, for the superconducting pairs or Cooper pairs. So what happens is that let's say that I have this correlation which is sigma dot p in my system, this kind of helical correlation. Now I'm getting to the barrier, and then I ask myself what happens. So if I am actually considering the lowest mode, so if I am considering the Py equals 0, then I do not have a surface to backscatter. So this is exactly this lack of backscattering which we saw for the surface states in the normal material. It's now coming into the superconducting material. So what happens is that the first mode, because of the time reversal symmetry, if I wanted actually to go back, so changing the momentum to the minus momentum would mean that I have to change spin to the minus spin. So this is not allowed if I have a time reversal symmetry in my system. So this means actually that I have to come and pass with the transmission equal 1, at least the first mode. And this is what we call superconducting Klein tunneling, and it has a large role here in understanding the physics as well as the skewness of the system, as you will see in a moment. So what happens is that the topological mode, as expected, because we can think about the tunneling of the Majoranas as tunneling of the, instead of charge of 2e, as we have usually for fermions, so the tunneling of the charge of just single electrons, so just e. And as you can see, for the single mode, the first mode, which is going directly in the normal direction through the barrier, we get a 4-pi periodicity. Now, for the all other modes, which are at some particular angle, what happens is that current phase relation would be actually 2-pi periodic, and we would have a gapped Andreev bound state. So this first mode, which is 4-pi periodic, is actually protected by time reversal symmetry and by the helicity of my system. And moreover, one can actually show that this mode, exactly, so this mode can be translated into the Majorana state if actually the system goes to the infinity. So if I actually put this normal regime go to the infinity, I could actually see that this is indeed Majorana. So from these two states, from psi 02 and psi 01, I can actually build a Majorana state. Okay, so this is indeed related to the topological, to the topology of the system. And then the question is how to really see this topological mode. So what happens is that one obviously needs to be careful, because in the usual ballistic systems, which is usual superconductor, normal superconductor junction, one also can see some kind of ballistic Andreev bound states. So one needs to distinguish between this ballistic Andreev bound states and the topological Andreev bound states. So as you can see, so the D here, so this is energy dispersion, and this is giving me plus minus delta cosine phi over 2, where phi is the phase difference between superconductors. And on the other side, we can actually see what happens for the ballistic junctions, and D here is the transparency of the junction. Okay, so if this junction is completely transparent and transparency is equal to 1, then these two formulas are equivalent to each other. So as you can also see here, so if these are the barrier, so if Z is equal 0, that means I have perfectly transparent junctions. So you can see that both of these supercurrents are the same for Z equals 0. And now we need to do something to the system. So what we need to really do is to change and modulate this barrier, which is in the middle between the two superconductors, to actually see that something new happens. So what one can see is that the supercurrent for the superconductor TI superconductor junctions actually doesn't go to 0 because of the superconducting Klein tunneling. So there is always a mode which is going through for large barrier. But for the usual ballistic junctions, what happens is that all the signal goes to 0, because obviously what happens is that this Andreev bound states goes, instead of being in the middle of the gap, is actually going to the boundary of the gap, and we do not see it anymore in the transport. So what happens is that indeed one could distinguish between these two things by putting a barrier, or one could also distinguish between the usual topological Andreev bound states and usual ballistic bound states by looking at the non-sinusoidal current phase relation. So this is supercurrent as a function of a phase, and we actually put a different strength of the barriers, and then what we do is we actually look how does it change. And this was also measured in the not so recent experiment, 2 years old, by Stanford group, which actually shows that indeed this kind of sinusoidal current phase relation can be measured. So the sinusoidal current phase relation indeed comes from this multi-scattering of this first mode, which is related to the superconducting Klein tunneling, and this can be measured. But let me focus on something which is newest. So the point is that the biggest problem with the DC current measurement and with the finding if the mode is 4 pi periodic or not is that one can have a quasi-particle poisoning, for example, and one actually doesn't know if one follows exactly these curves or if one goes like this. Yeah, so this is actually is depending on the Zener transitions and so on, quasi-particle poisoning and so on. So the question is, what is a better way of measuring of this topological 4 pi periodic mode? And we actually think recently about 2 different ways. So one way is actually looking at the thermal conductance as a way of detecting of this 4 pi mode. And another way is to look at the AC Josephson effect. So let me start with this thermal conductance and phase dependence thermal conductance. So this was done together with my postdoc Björn Soffman, and what happens here is we actually take the same kind of Josephson junction, but now we put a gradient of the temperature to the 2 superconductors. So now you should immediately start to shout, but I cannot put any kind of supercurrent through the superconducting gap. This should be 0, yeah, because obviously I have dissipationless particles in the gap. And yes, this is right. However, I can still see and actually detect this Andreev bound states through the quasi-particles which are above the gap. So what I am doing is I am looking at the quasi-particles above the gap as well as if I have a finite temperature, what I can do, I can actually take a Cooper pair, split it, and then recombine again on the other superconductor. So these are these 2 effects which actually give me information about the phase of my system as well as about the properties of the quasi-particles above the gap and density of states. So as you can see, because I'm changing density of states depending if I have a topological Andreev bound states or not topological Andreev bound state, I can actually see these things. Okay? So now instead of so now again transmission probability through the junctions, again the sum of the cross Andreev reflection and the normal co-tunneling, so it's the full transmission, and I can calculate now thermal conductance. So I have to integrate additionally on the energies. You can see I'm going now above the gap from delta to the infinity, and I can find the phase dependent conductance. Okay? So in this situation, I don't have a problem with quasi-particle poisoning because I'm not looking at this mode inside of the gap. I'm actually looking outside of the gap. Okay, so what happens is that I again can, and I have to always compare, because we were saying that there can be some kind of ballistic Andreev bounds inside of a gap. So again, I have to compare what's going on in my superconductor, topological superconductor junction, and what happens in the usual superconducting ballistic junction, which is just a trivial one. Okay? So as you can see, I can here draw a frequency as a function of a phase. And this is now for large Z, so meaning I have again the high barrier in my system. So what happens is that my topological Andreev bound state is actually always in a gap. So what happens is, because I am taking density of states, so this is here density of states drawn, so because I have always density of states of this Andreev bound state inside of a gap, then I have to take, in some sense, each sum of the density of states above the superconducting gap. So that's exactly what I see here is actually minimum above the gap. And because I see the minimum above the gap all the time, then actually my thermal conductance, which is proportional to the density of states. So my thermal conductance as a function of phase always will have a minimum here, okay, independent what would be a barrier. However, in this usual Andreev bound state, which is actually a trivial one, so what happens is that my Andreev bound states will actually try to go to the end of the superconducting gap. So what happens is that from the situation, so at the beginning, this ballistic Andreev bound state would also be in a gap, but then with the barrier, I will push it to the edge of the gap, and I actually can change the character of the density of states above, because now instead of having minimum, I am getting maximum, because actually this Andreev bound state in some sense is adding to the density of the states here and enhancing it. So what happens is that my heat conductance as a function of phase would actually have a maximum instead of minimum. So one can actually see even, and this is happening even if I have not only for 2D system, but also for the surface states when I have a lot of modes in my system because of some geometrical factor which comes into the calculation. And this could actually be used to distinguish between this kind of topological Andreev bound state and the ballistic bound state, Andreev bound state. Okay, so one could also, so we have also suggestion for the experiment. So this is in some sense in the line of the experiments which are done in Italy by Francesco, in Pisa, by Francesco Giasotto. So what happens is that one can actually put two normal leads here, and one can use two Josephson junctions, as you can see here. So more or less squid geometry with the tunneling barrier. And once again, one can have these two contacts and look at the temperature difference. And what happens is that obviously now one has to recalculate what happens, how looks the transformation of the heat to the bath and so on. But what happens is that if one take a usual processes, then one can calculate what is really the change of the heat as a function of flux, magnetic flux, which gives me immediately the phase relation in my conductance. And this is proportional, the pumped charge between these two contacts, to the difference of the temperature on the left and right. So what happens is that if I would take on the left the temperature of the 500 millikelvin, then on the right I would get actually modulation between maximum and minimum 20-30 millikelvin, and this is something which can be easily measured because in Pisa they can go to the resolution is less than 1 millikelvin. They can actually get it for usual junctions. So this seems to be a visible possibility actually to measure something. Okay, one also can think further. So what we are thinking further in this direction, of which is not related exactly to the to distinguish between different Andreev bound states, but one could actually go a step further and think about thermal switch based on 2D topological insulator. So the idea here is that I have two superconductors, and then I have a quantum spin Hall effect, so really 2D topological insulator, and then inside of this 2D topological insulator I have a phase. So again I have a magnetic field. So then what the main effect of this phase here is, at least from the point of view of orbital magnetic field, is what is called Doppler effect, meaning that depending, so the flux is different for the top edge state and for the lower edge state. So what happens is that I will acquire a different phase for the top and the bottom. So in general what it means is that I will start to close the gap. So if I was looking at the generally on the system, I am actually, with the phase I'm closing, for example, a gap for one spin direction or two spin directions. So this more or less means that without the phase, I have in general, I have a gap in my system. So I would not have any kind of thermal response, but when the moment I actually close the gap, I will expect a quite large response and quite large response of my superconductors, because again I am talking about quasi-particles. So I can make this kind of thermal switch by putting this flux and closing the gap in my system. Okay, so this is more or less the part which was concerning detection and understanding of these Andreev bound states in thermal transport. And the last part, which I guess I can go quite briefly about, is AC Josephson effect. So this is also what we did with Gloria Platero, who is in the audience. So again, this is, you saw this yesterday. So this is really Josephson junction based on quantum spin Hall insulator and on mercury telluride. And what we were interested in really in understanding why in some regimes you see 4 pi periodicity in this material and in some regimes you do not see it. Okay? So in the trivial quantum well, so meaning if the mercury telluride quantum well is actually very narrow, you see that you observe a usual Josephson emission, and as well the emission spectrum as well as the Shapiro steps with the frequency of Fj. However, if I go to the topological quantum well, what happens is that for small frequencies I actually see fractional effect. And this is in accordance with simulation which Fernando Dominguez. And as you can see here, so I can see the very large peak for the small frequency for fractional situation, and then I actually see that the frequency can become integer one. So one has to understand what it really means, because the point is that in these materials it's very difficult to, or at least I think it's very difficult to argue you always have a very large 4π periodicity, especially if you are doped and so on. So what one has to ask is, what happens if I had two different contributions, 4π and 2π, and if they are additive, one would expect it's very difficult to see actually 4π periodicity. So that's exactly what we did. So we now actually developed some microscopic models, but this is very simple macroscopic model, which is just resistively shunted junction. So it's consisting from the two supercurrents. And Shapiro steps exactly, it's a synchronization of my change of the phase or my frequency with the RF frequency or AC frequency in this case. And the way to understand some of these properties, we actually have a full phase diagram where actually 2π and 4π can be seen. Let me just briefly show it so one can understand from the simple mechanics. So more or less one can think about it as the sliding ball. So the M would correspond to the capacitance, and then obviously we have a part which is related to the change of the phase and resistance, and then U is actually the full potential which has the two supercurrents 4π and 2π and the DC current here. So one can actually see immediately that if one can think about it as two different slopes with two different periods. So now and let me just show you this. So if I think about the T1 and this kind of DC current is a big value, then the T1 is comparable with the T2, and I always see the 2π periodicity. So for example, for large current and for large frequency at the end, I only can see the 2π periodicity. Only in a case when there is a difference between these two slopes, and actually I can slide and stop only on the one of this minimum, I can see the 4π periodicity. So this means actually is that even if 2π component is much larger than the 4π component, as long as my DC current is comparable with supercurrent, I can have these two things very different, because as you can see, if my DC current and supercurrent is very close, it's 1/0, which is infinity, comparison with the finite value, which is related to the 4π. So in this regime, actually my system, even if the 4π is very small, 4π component is very small, it is very, very sensitive to the 4π component of my supercurrent. So let me just, because I think I'm running out of time.
Yeah, about maybe 2 more minutes.
Okay, good. So now obviously one can additionally, so over there I didn't have AC component of the supercurrent, but now I can add this AC component of the supercurrent, and then I just get an extra condition which is adding to the previous condition, which gives me the value of the supercurrent, which is exactly between DC current minus supercurrent 4π, which again tells me where exactly I should have a 4π component of my supercurrent. And one can actually do the full simulation. So this is what did Alexei. So we actually looked here exactly what happens at the different regimes and how one actually slides this ball here. And I think this is more or less like in Berlin, yeah, so you can not go through or you can go through. So now you can go through here the steps, and you can see that I am more or less stopping on both of these minima. Okay, so in this blue thing, this is actually usual situation. But if I go at the 4π step, then actually I can only stop at one of these minima, because you see I'm just sliding from the first one while I am just stopping only on the second one, so one can actually nicely see this. So we have the full phase diagram where we expect now no motion regime, where we expect no Shapiro steps, where we expect even Shapiro steps which are related to this 4-pi periodicity and formation of 4-pi supercurrent. And so let me acknowledge my collaborators. So as usual, Stanford Group Fiore, Stanford Group Experiment with Katrin Mola, experimental group in Würzburg, as well as Toin Klapwijk from Delft, which we are discussing a lot of the superconducting effects. So I would love to also acknowledge my group, especially Fernando, who was contributing a lot to these things, as well as Jan and Christian, which are sitting somewhere in the audience. And let me summarize. So we were talking about a few different things, but they were all related to the topological Andreev bound states, which one can generate in the system when one has proximity effect as with superconductor to the topological insulator. So we actually predict this non-sinusoidal current phase relation, which was observed in the experiment in Stanford. And then we think about the thermal conductance as even more sensitive way of observing helical Andreev bound states. And finally, we looked at the AC Josephson effect to actually understand in which regime the 4-pi component of the supercurrent is really visible and why is it visible. Thank you very much for your attention.
Thank you.